lecture on this polarized neutron reflectivity technique. And today I'm going application of this PNR technique about to study the interface magnetizers. And this is the outline. Actually, briefly, I have I will be talking about the examples I will be taking in this course. Okay, today's course. So first, we'll see because this technique, as you know, very sensitive to the interfaces, and as I said, it is very unique technique to get the depth profiling of the thin films and magnetic thin films multi-layers. So nowadays, people are talking about this interfaces where you are getting emerging phenomena like if you have two oxides layers and at interfaces insulating, and at interfaces you are getting high conductivity. So similarly, in case of magnetic films, magnetic systems, if you have two antiferromagnet system, so then PNR plays very important role materials or a paramagnetic or I mean other which are not ferromagnetic system where it is coming. So those things we will discuss today. Uh, I have taken few like three systems: emerging phenomena at interfaces and interface magnetization. Few systems which are already in literature and has been used. I mean, they have used polarized reflectivity to attack the kind of information they wanted because other techniques are not available, and only PNR can give that information. And then I will briefly discuss the one system which is called BFO LSMO heterostructures. In this case, I will explain this system, how we have studied this system using polarized neutron reflectivity. Of course, we also do other, as you know, we have to do other characterizations like structure characterizations, uh, macroscopic magnetizations. So we also use other techniques in addition to the polarized neutron reflectivity. Then I will take another example of and when they come to close to each other, and I have listed the information of the magnetic structure, depth dependent magnetic structure. And recently we did this kind of study on the ZD cobalt multilayer, and I will explain that. So as I was saying, there are phenomena or the interfaces which cannot be explained without using polarized reflectivity. I mean, where it is like one of the system which is there in literature. I have shown over here. Okay, so this is a multi-layer of CaRuO3, which is antiferromagnetic, and CaMnO3, which is again antiferromagnetic. And when this group from I think from USA, when they studied this material using macroscopic magnetizations like a squid, they found a hysteresis loop, which is signature of the ferromagnetic material. But they didn't have any component of ferromagnet. So it is antiferromagnet, but how to see that? And they also found there is an exchange bias. You know the exchange bias, which I have already said. Like exchange bias is nothing but when there is a shift of the hysteresis loop towards one of the magnetic field direction. So they found these signature, which clearly suggests there should be a ferromagnetic component present there. Then they went to the neutron scattering facility, and they did polarized neutron reflectivity. And you can see I have shown here measurement and the magnetizations. So they observe are the interfaces. This is CRO, this is CMO. Okay, CRO is this is the substrate. I mean, this is profile, and this is scattering density on top, nucleus scattering density, and this is magnetization at the bottom. So what they found are the interfaces. They obtained a magnetizer. So there are so many studies also available which says there is orbital reconstruction at the interfaces, which can change this magnetic element, the electronic configuration of magnetic element, and then which is responsible for the ferromagnetism. Okay, this is one. And the same group did study next year. They study this LNO CMO system, multi-layer again, and this LNO here is paramagnetic, and are in the film alone film, but both of, then you get the ferromagnets. Again, you can see this multi-layer here, LNO CMO on the this is the this is nucleus scattering line density profile, and this red one is the magnetic scattering density profiling of magnetizations. Then there is another phenomena which is there. So another system is BFO LSMO, and this BFO is antiferromagnetic. LSMO, you know, the ferromagnetic, and BFO is multiferric in the sense it is antiferromagnetic as well as it is ferroelectric. And this system I will show all the PNR data for this system, which we have studied over here also. And what is observed in this study is the thickness of the BFO layer at inter is large as compared to the earlier study where they found just 4-5 angstrom of large uh, larger thickness of BFO, turning out as BFO around 20 angstrom. The whole thin layer we got the ferromagnetism. And recently we studied these systems heterostructure, and what we found that we can get both ferromagnetic coupling as well as antiferromagnetic coupling in these systems. And ferromagnetic coupling means LSMO is ferromagnet. If the interfacial BFO moment is aligned along the LSMO moment, then they are say ferromagnetic coupling. When they are anti-parallel, so it is called anti-ferromagnetic coupling. what I mean to say, the interfacial BFO layer is showing ferromagnetism in the both cases. But the in one case where we are seeing FM coupling, the ferromagnetic moment is aligned towards the LSM. In other case, the whole thin layer of interfacial BFO, the ferromag the it in 2020, and we found, and I will explain this system and it is possible. And there is another phenomena which is there in the nature. Uh, yes, it is in the nature paper. So what they sorry, DI2SC, which is so this kind of things is happening at the interfaces. There are explanation, theoretical explanation why this kind of things there is you have a orbital reconstructions, ferromagnetism. Different temperature from these systems. We have to SC3, we have SN3, and this is the scattering line density over here. Okay, this is this one is the nuclear, and these others are so this the all for this layer. This is EUS. The magnetization is there up to almost at the room temperature 300 K, also little bit magnetized. But this layer, which is topological insulator here, this is substrate. Okay, this is topological insulator here. So at the interface region, if you see, this is the interface region. So they found there is a net ferromagnetism which is there up to the 120 K. So this is coming because of this proximity effect of a ferromagnet and topological insulator. As I said, this kind of depth profiling is possible only because of the neutron reflective. And this is the one of the study people have used PNR. Okay, so let us see another system. This is again a proximity effect, but here a superconductor and a ferromagnet. So what we get from the polarized reflectivity. This is YBCO, STO, LCMO. So you can see we have a substrate, then this is YBCO grown, this green one, then STO, and then for if we see the depth profile, this is our data over here. We have represented with NSA. It is nothing but it is called normalized spin asymmetry. It is nothing but the difference between the R plus and an R minus divided by R plus plus R minus. So difference by sum of the two reflectivity. Okay, which we are plotting over here. So this is basically reflectivity data only. And if you see at 50K, we found a magnetic dead layer over here. So there is zero magnetization in this interfacial region, which is around 35 angstrom in this case. Okay, and then a magnetization coming at 50K. But and this dashed line is fit when we assume uniform magnetization for whole LCMO layer. And suppose a magnetic dead layer model like this solid line, it didn't fit the PNR data. But when we assume a data, so it is saying we found a magnetic dead layer formation at the interface below superconducting transition. Same thing we obtained for another system where we have 150K and this LCMO has a higher TC around 300K. Still, we found the magnetic, there is a modulation at the interfaces. So here at 50K and 10K, I'm showing the magnetization depth. So this kind of study is only possible because of PNR. So okay, now I will go the first example. Okay, so as I said, BFO is the only room temperature multiferroic, but this multiferroic is not ferromagnetic, but it is antiferromagnetic and ferroelectric. Okay, and 1100K. But one of the disadvantages, because this BFO has on remarkably very good property for multiferroid, but as we see, the application of this material is not so far. The way it has come off during around 2000, so people thought that it will have a wide application in multiferroic based devices, but it didn't turn out that way because the main issue was the this is called what we call it lacks magnetic handling. Because for any magneto electric coupling, you need a high magnetizance. Okay, and then you can think of the coupling with electric field and other things. But BFO is anti-ferromagnet, so that is the big advantage. And for practical application, it has no net magnetize. Okay, as I said, it has a uncompensated or canted magnetizations, which is very small, 0.03. It is two order down the magnetization of iron metal. Okay, so it is too small for any applications. So then people thought of, okay, if BFO doesn't have a ferromagnetic component, and we want to talk about the multiferric effect, magnetoelectric coupling, then we should have some ferromagnetism in these systems, which we can couple with the ferroelectric property of this element. Then people thought of making of this kind of heterostructure, where one you will make a ferromagnet, which is around room temperature ferromagnet. Okay, it has because bulk LSMO has a 350K transition temperature. It is a spin polarized system. So if one can get any ferromagnetism in BFO, that will be very good for application wise. So people thought of making this kind of hydrostructures. So I will explain this, and I will see we'll see when they found there is a interface ferromagnetism in BFO system and heterostructure. And this study was mainly based on the synchrotron based study, where you have you do XMCD and you sit at one particular how it the somehow corresponding magnetic contribution for those elements in the system. And they also found the exchange bias. You can see when you applied a field cool plus field land here, what they say, this interfacial, this induced magnetization is confined at the interfacial region without doing the any region, and the magnitude of spin magnetized BFO layer adjacent to this is likely even higher than this value. They found okay, 0.03. Okay. Then around 2014, we studied the system. We made a multi-layer PFO superlattice of these systems of different thickness, and we did all kind of characterizations like this is LSMO BFO and 8 bilayers of this system. Before doing PNR, we did all characterization possible characterizations tech selectivity, and here also we found multi-layer structure. Okay, and then we did TM also. A TM, so very nice multi-layer structures. Okay, 5 complete characterization. What we found depth profile NSLD, because NSLD as time was the we found from X-ray reflectivity the electronscattering density. So we found this magnetization around 80 EMU per cc for BFO layer, which is thicker. I mean, this is not the one unit cell; it is 5 unit cell of the BFO, and the whole BFO is showing that 5 unit cell. I think ferromagnetic magnetizations, and which is ferromagnetic. We model this data with uh, different models, like assuming there are in the BFO whole 5 unit cell thick sample till layer. Okay, in this multi layer. We also found here in this study, what we found that here we have drawn this x-axis shows this F iron layer, and this shows the interface region. This is one of the interface, this is another is interface, and we found there is a possibility of getting both ferromagnetic, this is positive value, as well as the anti-ferromagnetic coupling in these systems. So this happens when this bismuth comes in between the two ferromagnetic element, then we have a ferromagnetic coupling. But when these two ferromagnet element are separated by La, then we will have a antiferromagnet. Or in fact, recently we did this and we found same thing. And also what is happening, what happens, because this LSMO BFO is a polar element. What happens if you see the thin films of this, we get the layers, and a surface termination. Surface termination is at the interface. There's a termination. There is a the BFO whole things makes two kind of layer like FeO2 and BiO and MnO2 like this one, and they have different electronic configuration. Charge balance, if you see, it becomes zero. So at the interfaces, there are two kind of termination happens in this. Okay, so depending on as this first principle calculation also suggested, when when this iron and Mn or the interface is separated by bismuth, then we will have a ferromagnetic couple. But when this iron and Mn is separated by L or Sr element, then we will have antiferromagnetic. This is exactly which we have obtained, and this study said uh, ferromagnetic and antiferromagnetic coupling. Then recently we have grown so many samples. Four are listed over here. BFO, and one tri-layer. So LSM of BFO, these are different thickness over here, and the roughness at the interface is shown here, and then it is named like S1, S2, S3, S4. S4 is our tri-layer, or other are bilayers. And we did all characterization technique as explained earlier. So one of the sample I will explain here. Suppose S1. This is S1 where we did the polarized reflectivity at different temperatures. 100K, 150K, 5K, and this is NSA, which I was saying nothing but the from the reflectivity data only. So it is a difference between two devices, and minus divided by sum of two reflectivity. This is so for R plus and R minus for 300K data we have a straight line because there is no splitting of R plus and R minus 300K. It suggests there is no ferromagnetism in this system at 300. But if you see 150K, there is a difference. And this, if you see, this is the nuclear scattering length density, this red one as a function of depth. So here here it is MZ, this is L, LSMO, this is L, BFO layer, and this is kind of nuclear scattering length density. And temperature dependent magnetization depth profile. If you see, for 300K we don't have any magnetization, so it is 5K we have magnetization for LSMO positive, and we got a negative for interface layer, which is around 30 ms. Okay, and you can see these are the different models for 5K data. We assume different. So this 5K, we assume this is the LSMO layer. This is interface. This interface is shown over here. This is BFO layer. This interface part, which is around 35 angstrom. From here to here, it is 35 angstrom. This is LSMO. So you can see when we consider zero magnetization for here, this black one is there. So this is not fitting this PNR data very well. When we assume this ferromagnetic nature, means both the LSMO and interfacial BFO layer has same magnetism along same direction, which is called ferromagnetic alignment. So still we didn't get the best fit for the PNR data. But when we assumed this there is an anti-ferromagnetic coupling, this LSMO and BFO moments are aligned opposite to each other only for interfacial layer of 35 angstrom, then we get the best fit. So this says there is anti-ferromagnetic coupling. But when we studied another sample, another bilayer sample, which I've shown in the table one, listed named as S2 and S3. Okay, strand BFO, we found a positive magnetization for the interfacial BFO layer, and which is showing the ferromagnetic coupling. And as discussed earlier, I have shown this 5K data here, and different model is plotted over here for two samples. And one samples we get best fit when there is an anti-ferromagnetic coupling at the interface. Another sample we get best fit when we have a ferromagnetic coupling at the interfaces. So what does it suggest? That there are these two samples, so different type of coupling. And as I said, this is happening because at the interfaces we are getting two kind of surface terminations, which gives the different kind of coupling. Okay, and in fact there was another study from this kind of things, but with the squid measurement, what they found, when they have a ferromagnetic kind of things, they have higher magnetization here. So this heterostructure A is this kind of termination. This is heterostructure B Okay, this is B1, another kind of termination which gives the antiferromagnet as per the our this first principle calculation. And you can see the total magnetism so that net magnetization is increasing for this and reduce for this one at low temperature where there is a coupling. So this is the summary for this part. So we found which I have already said, like we have both the type of coupling, okay, and these things are reported over here. So I will quickly go to the next system, which is superconductivity driven system. I mean, driven magnetic uh, 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 magnetic modulation are the interfaces. And here we are talking about the YBCU, STU, LCMO, and LSMO heterostructures. So you know superconductor, YBCU. These are the copper plane which is responsible for superconductivity in this. And TSC, the superconducting transient temperature is 92 K for bulk YBCU. Okay, and also for film, sometimes it is that. But these are the aeromagnet which has PCs around. In the bulk it is 260 and 340 K, and thin films it vary depending on the thickness and other things. It varies. It becomes around 300 K, or it can go to 170 or 150 for LCMO, and for L 300. And they are fully spin polarized. They show fake phase coexistence and a colossal magnetoresistance. These properties, these kind of ferromagnet source. Okay, so let us see when we what happen when we bring close the superconducting and the ferromagnetic. Okay, so we know superconductor there are Cooper pairs, and then we have a ferromagnetic spins over in the ferromagnet. So what is happening at the interfaces? There are so many phenomena related to this kind of proximity, which has been studied very I mean large. And then there is a inverse proximity effect. There is endo-reflection, spin injection, spin accumulations, reflection of all this, these phenomena happens. So let us see. We will consider. Will explain something about this one. So if you see, just make a YBCO and LCMO multilayer. This is nice study when they have made this superconductor and ferromagnetic multilayer. Uh, this is spin up. This blue, red is the spin down reflectivity, and they found there is a ferromagnet. Okay, because the difference between these two reflective pattern gives you the depth profiling. And here they have shown one of the layer of this is two interfaces. They have shown LSMO, YBCO. So this is nucleus catalytic density. Okay, this one is LCMO, and this is YBCO. Okay, and these are the two interfaces. Okay, and this is the magnetic SL, magnetic catalytic density. And you can see at this interface there is a magnetic dead layer. This is LCM only. But at below superconducting transition, what they found, it is giving a magnetic dead layer. There also magnetic dead layer, but thickness is little bit different. The thick it is around uh, this is around 12 angstrom. This is around maybe 5 angstrom or something. But what we found, low superconducting transition, there is a magnetic depletion. So ferromagnet becomes some kind of uh, uh, system which has a magnetic moment zero, average magnetic moment zero. So it can be antiferromagnetic, it can be paramagnetic, and it can be just magnetic dead layer. Okay, so we also did same thing when we YBCO and LSMO instead of LCMO, LSMO layer by layer. So we also found a below superconducting transition at 10K. So this is YBCO, and this is interface here. Okay, this is nucleus catalytic density shown over here. This is MZO, YBCO, LSMO, and this is the magnetization depth profile here. Okay, This is magnetization, and this is the interface where there is a YBC on this side and LSM on this side. And you see above superconducting transition, this red one is at 100K uniform magnetization for this LSMO layer. But at 10K, you see there is a magnetization, inverse magnetization happen in this case, which is around, as I said, around 35 angstrom thick, which shows there is a reduction of magnetizations in LSMO when it goes below the superconducting transition temperature. Okay, but this is just the proximity effect. Now, what we did, we we thought, okay, why don't we try and see when we put a STO, which is insulator, again oxide insulator layer in between the superconductor ferromagnet. So what will happen now? Because in principle, this insulator should stop if something is going from, like Cooper pair is going from here to there and disturbing the magnetizations. Then once we put this STO, it should stop that, unless there is a Cooper pair tunneling from here to there, and then they are disturbed. And let us see what we found from the PNR study. Again, for this study, we have done all the characterization technique. Here, I'm just showing the PNR study and the result we obtained from PNR. Okay. So again, 300K, there is no ferromagnetism in this system. At 10K, you see, there is quite ferromagnetism. And here I'm showing NSS, nothing but the difference between these two. Okay. So if you see, this is nuclear scattering density on top, and it shows substrate, then YBCO, then STO thin layer, then LCM. So at 300K, we don't have any magnetization. And at 10K, what we found there is a magnetic dead layer over here at the interface, or the STO interface. This is a magnetic dead layer where there is a no magnetization. This is magnetization curve. There is no magnetizations in this region. Okay, and that suggests, that clearly says, yes, there may be something happening in this system also, though we have put the STO in between. So this can be best explained when there is a tunneling of the Cooper pair is possible in this kind of system, which is disturbing the magnetization below superconductor. Same thing we did with LSMO. Okay, and we found, again, we did temperature dependent reflectivity. So we found at below superconducting transition 50K and 10K, we have this negative magnetization here. Instead of magnetic dead layer, we have antiferromagnetic coupling. I mean, the magnetization is opposite to the rest of the LSMO layer. Okay, so these things clearly suggest there is a tunneling of the Cooper pair happening below superconducting transition temperature in this system. Okay, which is modifying the magnetization depth profile at the interfaces. And this study, we also changed, I have not shown over here, we have also changed the thickness of this STO layer and shown the effect of what is, if we increase the thickness of STO layer, what will happen, the thickness of this, what will happen, the magnetization depth. We obtained similar kind of magnetization depth profile, but now the magnetic depletion layer, where we are getting either magnetic dead layer or this reverse kind of magnetizations, that with with increase of this STO layer thickness, we are getting decrease in this depleted layer. Okay, so that also suggests, yes, because in tunneling same thing happen. If you increase this barrier thickness, then you will have less tunneling, and which will affect our magnetizations, which will affect less our magnetization magnetization information in the at the interface of this system. Okay, so these two system says, without PNR, we cannot get this kind of information for these kind of systems, which are complex oxide systems, in which one case we found there is a ferromagnetism, and that ferromagnetism is not very small, but it is, we found around maximum ferromagnetism in one of the BFO LSMO system. The interfacial BFO layer was showing a magnetization of around 180 EMU per cc, which is quite high as compared to the canting moment. Canting moment, I just said maybe 10 EMU per cc or something. So this is quite large. and one can, if one can increase that magnetizance and also increase the interfacial layer thickness by means of some butterface and other things, like if you change the strain and other things, strain is the one factor, then you can really get the application of those materials, which was believed in earlier that these multiferroic system will give you very large application in multiferroic devices. Okay. So let us now move to the another system, which where we are using another property of another strength of the polarized neutron reflectivity, which is when how to get depth profiling of the magnetic structure. Till now, I was saying magnetic moment. How we get the magnetic moment, which are totally aligned along the field direction. But there are system you can study. There are system when there is a magnetic structure is changing. All the magnetization in the whole layer is not aligned with the field, and there is some rotation and other things happening. Then we have to get that magnetic structure, and that is can be done best by the polarized neutron reflectivity. One of the system which we have studied is rare earth and transition metal, ZD cobalt multilayer. Okay, and you know GD is rare earth, and this cobalt is transition metal, and GD is ferromagnetic, and TC is around 273 K. Okay, and cobalt has a, I mean, it has a, it is ferromagnetic at room temperature and higher TC around more than 1000 K. Okay. So these system, if you see the literature, if you measure the magnetization as a function of temperature, the typical magnetization we get like this. So what happens at room temperature, where only cobalt is ferromagnetic, only cobalt is ferromagnetic, GD is non-magnetic. So cobalt is aligned along the field direction, applied field direction. Okay. Then when you decrease the temperature, now GD moments develop. But these systems, GD cobalt based system, they show a higher interaction. This coupling at the interfaces, which is antiferromagnetic. Okay, that exchange interaction at the interface for this rare earth and transition metal is quite high and antiferromagnetic in nature. I mean, it is negative for this kind of system. So what happens when GD develops ferromagnet? The ferromagnet of GD layer is opposite to the cobalt layer in this region. So we say cobalt island because cobalt is still along the field direction. So this state is called cobalt island. When we further decrease the temperature, so now we get a compensation where there is a complete complete total moment becomes near to zero when cobalt moment is along one direction and GD moment is developing, and both are neglecting each other, and you have a about zero magnetization. Though in this case we didn't get the zero magnetization because we are getting additional features which will come to later. We'll see from the PNR study why we didn't get the zero here when there is a complete uh, compensation, but we didn't get the complete compensation over here. But when you further down the temperature, now what happens? The GD moments are which are increasing, it becomes aligned toward the field, and cobalt become opposite to the field direction. So we have different kind of magnetic phase along the temperature. Okay, and was our aim to study the magnetic structure, what is happening basically here, because this squid data won't see anything. It is just saying there is a compensation temperature, and maybe one magnetic moment is increasing, other is increasing other direction, which is compensating here, and then something is happening. So you cannot explain this thing unless you do the magnetic structure of both the cobalt and GD as a function of temperature. So in this case, since this exchange interactions highly depend on the interface property, so what we did, we grew three samples, and here to change the interface property, we have grown these samples by sputtering method, but different argon pressures, which will modify our interfaces and which will modify the exchange interaction or the interfaces. Okay, first sample was grown, which was best sample. It was this GD cobalt multilayer grown on silicon. GD cobalt around 8 bilayer of that. It was grown around in the organ pressure of 0.2 Pascal. In second film for which we will say S2, this is S1, this is S2, another multilayer. Now we have double this pressure, and which will uh, destroy our interface. I mean, interface morphology will change, and then we'll have different kind of interaction, which we'll see whether we are getting that or not. And another sample here, we have grown first 4 bilayer with one pressure, and another 4 bilayer by another pressure. We didn't want we have grown these two in the single film because we know when we change, we grow same thing to another film, which we did here. So that itself, I mean, environment can give the can change the interface property, but we don't want. So we have grown this aperiodic multi-layer kind of things in this system. Though we have kept thickness constant for all these systems when we grew these kind of three samples. The thickness for GD and cobalt are fixed for three samples. Only we have vary the parameter like growth parameter. So as I said, we have done all this characterization techniques like XRD. So we found GD peaks and cobalt peaks. Then we have done X-ray reflectivity. Nice. This is the S1, first one, best one. Bilayer. This 8 bilayers are there. This is for uh, cobalt, and this is for ZD, and this is gone on silicon. And if you see for S2, we are getting higher roughness at the interfaces, and for S3, first roughness is small, but which we were grown at higher pressure, organ pressure, the roughness further gone away. So this clearly, so this is structure or depth dependent structure study clearly shows we have different morphology at the interfaces for these three samples. Okay. Now and these all this study has been reported in this pictures. Okay. So typically we assume GD is 150 angstrom, cobalt 100 angstrom, and 8 bilayer of this. This was our sample, and we have, as I said, three samples we made like this. Though X-ray reflectivity state GD is 135 angstrom and cobalt is around 75 angstrom. Okay. So let us see next what we did is this one. What we did is again magnetizers. So for S1, which was grown at lowest organ pressure, so we can see that this is FC and ZFC. There we didn't see any splitting of FC and ZFC, and but compensation temperature around 125 for S1. Then we did magnetization for S2, temperature dependent magnetization, and you can see we found this coupling compensation temperature at higher temperature, little higher. One earlier it was 125. In this system we found 140K, but below compensation temperature we found splitting in the FCZFC, which clearly suggests there may be some kind of this sort of things happening, which is resulting in this split. Further, for S3 we found a little bit higher compensation temperature, 150K, and also uh, uh, the the difference between FC and ZFC is large below this compensation temperature. Also, the net magnetization or room temperature is also reduced because of this interface roughness and other things. We have lower magnetization for cobalt itself. Okay. And if you see the MH curve for these three systems, you'll see temperature dependent MH curves. You'll see really different nature. Okay. So S1, this is 300K, then 250K, 200K, that way. So at 300K for S1, nice ferromagnetic peak, which at lower temperature, we are just getting a change in HC, increase in HC. But when we do around 125K, we have further this change. But when we go further down the temperature, we have a shift in the magnetism, which is showing the exchange bias. In case of S2, again, we have a little bit different stresses loop, which shows kind of asymmetry. Okay. And this asymmetry, as well as which increases, this asymmetry increases at low temperature, as well as there is exchange bias. And if you see along the this y-axis, also we found the shift in the vertical direction also. Here there was no shift in case of S1 vertical direction, but in S2 we get the vertical shift also. We are getting horizontal shift because of action bias, but we also got the vertical shift in this hysteresis loop, which suggests there is additional pinning, maybe due to the roughness at interfaces we are getting. And S3, it shows quite different. We got two kind of loop over here. One is like this. This is addition of two loops here, which is increasing. Then we found, and at low temperature, we got a nice hysteresis loop with a large Hc. So we can see the different. But this is, I mean, this is well known. We expected this way. That's why we have grown the samples like this. But our main aim was to see the how the magnetic structure changes. Okay. Then we did the transport measurement also. Transport measurement, you can see at higher temperature, it is like any it's like for any ferromagnetic system, we get this peak, which is due to the corrosive field in the whole three system. But near to this is this is compensation temperature. This all three. This is for S1. This is for S2. This is for S3. And for S1, you can see we are getting asymmetry. So this red one is while warming the sample from while going to negative field to high positive field, and blue is the when we reverse the magnetic field direction. So this is MR versus H. So we are getting asymmetry. You can see this is going up, this is going down, and this asymmetry decreases in S2, but we didn't get that asymmetry over here. We get additional things in the MR data. And when we go for low temperature, then it becomes again a uniform. Okay. So to see all this kind of structure, we have done polarized neutron reflectivity with spin analysis. Okay. And this is that this these measurements has been done at ISIS Rutherford Laboratory Lab at UK, where we have this kind of system, this kind of instrument over there. This I have already explained you. When we need a polarization analysis, what kind of components we need. So we need a polarizer, then we need a flipper, then we have a sample over here. Then since we want the spin, both the spin flip R plus plus, R minus minus, so we need a flipper here as well as flipper here, because we want to analyze the reflected neutron, whether we are getting R plus plus, okay, and then a analyzer over there. So typically, and we had a two-dimensional, we have an area detector. This is time of flight technique, and we have an area detector. So simultaneously, we measured specular and off-specular reflectivity. And here again, I just to remind, off-specular is the when angle of incidence is not equal to angle of reflection, and specular is when angle of incidence equal to angle of reflection. When we have off-specular, we have QX component also. QX and QZ, both components are there in case of off-specular. But when we have just specular, we have just QZ component. And typical reflectivity in a array detector from the sample for S1 at compensation temperature 125 K R plus plus reflectivity, when we are putting a spin up neutron in the sample and collecting only spin up reflectivity. So that shows here. And when we did a spin flip, when we are putting a spin up neutron on the sample and collecting spin down reflectivity, and we found this kind of structure. And you know, this plot is nothing but a map QX QZ map. Along X direction, this is QX, along Y direction, this is QZ. And this at QX equal to 0, QX equal to 0, we have only QZ. Okay, so the specular reflectivity is the intensity at Qx equal to 0, and function of Qz, this is the specular reflectivity. And but when there is Qx is not equal to 0, but still we have intensity like this. So this is off specular intensity, whereas the intensity along this direction is specular. So we found for a spin flip channel, we found Q's of specular reflectivity, which is, you know, spin flip is due to the magnetic region. That's why this of specular reflectivity, this Bragg sheet, what we call this intensity map we are getting only at the Bragg peak. This was the Bragg peak portion. This was first Bragg peak. This was second Bragg peak. And if you see the specular reflectivity, this is the first Bragg peak. So this is first Bragg peak. This is second Bragg peak. This is specular reflectivity. We are just collecting QZ function in the previous slide. Yeah. So the specular reflectivity is this intensity here, which is I am plotting over here for all the three fields. And at 300K, we didn't have any spin flip component. So whole, and since GD is non-magnetic and only cobalt moment we are getting, and this is I have plotted here the total magnetic and nuclear part 300K. But for other temperature like 200K, 200K, S1, S2, we didn't get any spin flip signal. This is red one is R plus plus, blues R minus minus, and this one is the average of spin flip component R plus minus plus R minus plus. And from this analysis, because we have below compensation temperature, we have this spin flip part, and what we have got is this kind of magnetic structure. This is a one bilayer of GD and cobalt, and you see the magnetic moment, how magnetic moment in plane magnetic moment. So for fitting this data, we have assumed like this is GD, this is cobalt, like this spins are rotating and making a spiral kind of things, helical structure as a function of that. Okay, so it is rotating when thicknesses we are moving from bottom to top. So that way, this kind of structure we have considered and obtained different structure at different temperature for all the films S1, S2, S3. So this is the advantage of doing this kind of study. And if you see, we have assumed different structure. This was the final result which gave the best fit. But if you see for S2 at 140K, this data, we have assumed different kind of structure, and you can see different kind of fit is coming, which is not at all good. This is one of the like cobalt align. We assume both cobalt and ZD are opposite to each other. This one structure we have assumed this, then we didn't get the fit for this system clip, and as well as these whole data we couldn't get the best. So we have discarded all these structures and got the best fit for this all these samples, but this one. So we found at the compensation temperature we had a helical structure where all the moments are changing as a function of depth in both GD and cobalt. And this has a wide implication as a application point of view. One can think of a lot of application if we get this kind of helical structure in the these kind of systems. Okay. Then here I have shown that this which I just now I explained this QX QZ map for all the samples, and only for S1 we got this kind of uh, at the compensation this kind of Bragg sheet which says they are vertically correlated. The moment are vertically correlated, and for other system also we didn't get, like for S2 and S3. S2 intensity was poor. This whole thing is for S1 at different temperature. This middle row is for S2 at different temperature, 200K, 140K, 5K. And this is for S3. Okay, and you can see the different the simulated profile and the experimental profile, and you can see what is the so different kind of structure which says suggests which says the what kind of magnetic information we get from this system, and which shows quite different for these three samples. Yeah, I will stop here. So if you have any questions. So we'll have on Friday one tutorial session, and Dr. Basu is here. He want to say something, and on Friday we'll do some tutorial about this reflectivity part. Okay, at that day we will do whatever. If you have any query, please write to me. Thank you.
So, good afternoon, friends. So, this was the penultimate talk of this course. Friday, the formal lectures for the course will stop, and I will start sending back the marks for your assignments which you have submitted. And I find that you have done reasonably good, but some of you have not submitted some assignments, and that is important because unless you submit the assignments, I cannot go ahead and hold viva voce exam for those people and cannot give you credit. So that's my request that please submit the assignments as early as possible. Dr. Surendra Singh has also given five problem short assignment. So now all the module assignments are there at Anuvidya. It is you for you to submit them as early as possible because there are two issues. One is that I need to hold a viva voce examination, a short viva voce examinations for the people whom I like to give who have been attending the course for credits. And also we will have a brief concluding session, most probably on 8th or 9th of February. I'll get back to you on email and inform you. And I hope that these last two modules, some of you at least found them very interesting and important because today many of you will be working on thin films. And when you work on thin films, several techniques come very handy. Polarized neutron reflectometer is one of them. And some of you will be also working on mesoscopic structures. And for them, whether you are in physics bordering on biology, chemistry, or metallurgy, or even geology sometimes, because this technique, small angle neutron scattering, can look at pore sizes also inside rocks and all. They will prove to be handy. And I also like to have right now. I can tell you feedback from you. One part is that you can give the feedback to me on email. Yeah, at neutroncourse at gmail.com. I will also like to have some of you speaking during the this concluding session as feedback. So with this, today we will close the lectures, and thanks a lot.